Hi, welcome again to Business Mathematics 1 courses. So I'm Eric from Business Mathematics Teaching Team from Mathematics Study Program, Faculty of Mathematics and Natural Sciences, ITB. So for today, we are going to discuss Introduction to Probability. Before we are going to proceed with the definition of probability, it is a good time for you to review on counting rules by doing these exercises. Okay, now we are going to define the probability. Now maybe we can have an experiment. It's done by tossing a coin. So the sample points are the outcomes or the result, that is heads or tails, H or T. And the sample space is the set of all sample points. S equals H comma T. S is the sample space. And the event is a subset of sample space, that is the empty set, set that contains H, set that contains T, and set that contains H and T. What is the sample space of this? Tossing two coins, tossing three coins, rolling a die, rolling two dice. We are going to discuss that and how we can have the sample points. How can we have the sample points for these four events? So something to be kept in mind that we will just only looking at an experiment with finite sample points. For experiment with infinite sample points will be discussed on a more advanced courses. So there are some ways to obtain the sample space, that is by table or with tree diagram. Because an event is a set, then we can see the union, intersection, or the complement of two events. Sample space in which the outcomes are equally likely are called uniform sample spaces. Example, if I'm tossing a coin, if I'm tossing a fair coin, so the outcomes will be equally likely. The same, if I'm rolling a die, a fair die, so the outcomes are equally likely. So the sample space is usually called the uniform sample space. Okay, this is how we find all of the sample points of an event. So this is from tossing two coins. This is the first draw, the first tossing, and the second tossing. So if I have TH, this means that I have tails for the first and heads for the second one. This is for the table for sample points for when we are tossing three coins. And this one, this is the tree diagram for tossing two coins. The tree diagram for tossing three coins. Here I have HTH. This one is the same as this. You can see. So both you can use both tables or tree diagram to find all of the sample points from an event. So this is the definition of probability. Probability of an event E in a uniform sample space is defined as ratio of number of wanted events with number of possible events. That is the probability of events E is the number of wanted events divided by the number of possible events. And here are some properties of the probability. The probability of an event should be between 0 and 1. The probability of empty set or event that cannot be happen, that is 0, and the probability of the sample space must be 1. Probability of all that happens is 1. Probability of E complement is 1 minus probability of E, and probability of E union F is probability E plus probability of F minus probability of E intersection F. And this comes from the Venn diagram. Okay, and in case of the intersection of E and F is an empty set, we call the events E and F are mutually exclusive. And the probability of the union is just probability of E plus probability of event F. Without this, because the probability will be 0. Okay, probability can also be defined through other ways, such that relative frequency, you can read it thoroughly and in the textbook. So this is the probability problem 1 corresponds to the review problem number 1 for counting rules, and this one also the review problem the probability problem 2 corresponds to the review on counting rules number 2. So when I want to find the probability of the event, there must be a boy. So we have to know the number of ways that we want to get four children from 10 children when there must be a boy, divided by all possible outcomes. Remember, the probability of this event is the number of wanted events divided by the number of possible outcomes. So spend time to find out what is the probability of all of this problem and all of this problem. Okay. And then we are going to define what is the conditional probability. We are going back to the urn problem again. An urn contains 7 balls, that is 3 red and 4 white balls. What is the probability of getting 2 red balls without replacement? As you know, this is numbers of ways to pick 2 balls from 3, 2 out of 3, from all possible outcomes, pick 2 from 7 balls. So I have 3 over 7 times 2 over 6. And if I look at it carefully, 3 over 7 is just the probability of taking 3 red from 7 ball. And then 2 over 6 is probability of getting red ball for the second row, given that the first row is red ball. So I have the red ball is just 2 out of 6. So if A is the event of getting the red ball for the first row and B is the event of getting the red ball for the second draw, so this is the event of getting this and getting this. This is the event of A intersection of B. And what is this? 3 over 7, the probability of A. And what is this? 2 over 6, probability of the second row is red ball, given that the second row is red, given the first row is red. Okay, so I can define the probability of B given A is probability A intersection B divided by probability of A. So I have this as our conditional probability. If A and B is two events, it will satisfy this relationship if we have conditional probability. And we can switch this probability of B given A is probability of A intersection B or B intersection A, the same, divided by probability of A. This is A given B, so probability B, or if I have probability B given A, so this is divided by probability of A. And geometrically, when talking about the conditional probability, the sample space becomes smaller because the sample space is just the event B. Okay, yeah? Okay, now we are talking about independent events. We are looking at the same problem, the urn problem. A and B is defined by the same. So I have probability of the second row is red, given the first row is red, is the probability of A intersection B divided by the probability of A. So the question is, what is the probability A given B? Is not as easy as you think, isn't it? It's because the event of getting red ball at the first row depends on the events getting red ball or at the second row. And the events A and B are called not independent events. Not independent events. Because A depends on B and B depends on A. Okay, yeah? In case that we have independent events, A doesn't depend on B and B doesn't depends on A. So when A doesn't depend on B or B doesn't depend on A, the probability of A given B is just probability of A, because A and B just an independent events, are independent events. Okay, so this is an example of independent events. You can look at it. So if we are want to check whether two events are independent events, we can check as this. Probability of A intersection B by conditional probability is probability of A given B times probability of B. If A and B are independent events, so this is the same as probability A. So to check whether two events independent whether two events are independent or not, we can check whether the probability of A intersection B equals probability of A times probability of B. If this equals this times this, so the two events are independent events. We can look at this problem. Okay, this is rolling two dice, and we can look at the sample points is this. The probability of event A. What is event A? Number 4 appears on the uppermost of the first die. So this is for 1, for 2, for 3, for 4, for 5, and for 6. So 6 out of total sample points is 36, 6 out of 36. And if B is the sum of number falling uppermost is 6. The sum is 6, or this one, 2 plus 4 is 6, 3 plus 3 is 6, 4 plus 2 is 6. So I have the diagonal. The diagonal has the sum of 6. So what is the probability? 1, 2, 3, 4, 5. 5 out of 36. And what about A intersection B? So it must be in this, but it must be in this also. So the intersection is given by 4, 2. So this is 1 out of 36. So I have 1 over 36. What about this one? Number 4 appear on the uppermost of the first die, given that the sum of numbers of falling uppermost is 6. So given this means that the sample all of possible outcomes is just this one, this one, this one, this one, this one, this one. So the possible outcome is just this one, given B. So the possible outcomes, the sample space now is getting smaller. So the sample space just contains this one, this one, this one, this one, and this one. So number 4 appear on the on the first die is just this one. 1 out of 1, 2, 3, 4, 5. 1 out of 5. And you can do the same for this. If we are looking at whether A and B are independent events or not, we can look at the probability of A intersection B is 1 over 36, probability of A is 6 over 36, probability of B is 5 over 36. I know that 1 over 36 doesn't equal 6 over 36 times 5 over 36. So there are two dependent events. They are not independent events. Okay, yeah. And lastly is the Bayes theorem. Bayes theorem relates how to calculate probability B given A if given A given a probability of A given B, or the other way around. So back to the earn problem again. A is drawing red on the first row, B drawing red on the second row. So we know a probability of drawing red on the second row given that the first row is red. And I know the probability of the second row is red given that the probability of the first row is not red. Probability A, red in the first row, I know. Not red in the first row, I know also, okay? Probability of A, what is this probability of A? 3 out of 7, and this 4 out of 7. Probability B given A, B given A, B given A is just 2 out of 6, and this is just 3 out of 6. Okay, yeah? And I have probability of A given B. I can calculate. Okay, I don't know this, but I can calculate by using the conditional probability formula that is given by this divided by probability of B, because the given is event B. So what is probability A intersection B? I can use the same formula for conditional probability and give you this probability of B given A times probability of A. What about probability of B? Probability of B is probability of B intersection of A plus B intersection of A complement. Okay, yeah. And what is probability B intersection A? Is just this one. What about probability of B given A complement? Is just probability B given A complement times probability of A complement. Okay, yeah. So I know the relation between A given B with B given A and B given A complement. We can generalize this problem in the next example. But this one you have to remember to uh, to to learn more about Bayes' theorem. It is easier that if you draw the tree diagram first by defining what is A, what is B, and what is A. This is the probability of A event A happens, that is 3/7, and what is this is probability of B given A, 2/6, probability of B complement given A, 4/6, 2/6, 4/6. So if I have B given A, this is just 2/6. Probability of A is 3/7. So the upper one is just 2/6 times this. And what about this? Probability of B given A complement, B given A complement. So 2/6 times probability of A complement 4/7. Okay, yeah. And you can define what is A, what is event B, what is event C, what is event D, what is event D complement by looking at this problem. Define first what is A, B, C, D complement, and find out what do you want to know for the probability of this one. And using this tree diagram, you can solve this Bayes theorem. Okay, try this on your own. Okay, so today we have talked about the probability, definition of probability, the conditional probability, independent events, mutually exclusive events, and the last one is the Bayes theorem, the relation between a probability of B given A and probability of A given B. Okay, thank you.